This is Variational Surface Cutting by Nick Sharp and Keenan. Today, we'll talk about low distortion surface cutting. And by surface cutting, I mean given a surface as on the left, we wish to compute a cut network gamma as shown on the right in red. And furthermore, we want the surface to be easy to flatten out after being cut. And when we talk about cutting a surface, I want you to think less about texture mapping, like you might have heard of before, and more about this chair. Given the chair geometry, one must decide where to place seams to enable a patch layout with little stretching. How would you design an algorithm for this task? The remarkable outcome of our work is that the task of low distortion surface cutting can actually be modeled by the simple flow you see here, which was not previously known for this problem. We'll dive into this over the remainder of the talk, but essentially what it says is that given any cut network gamma, we can optimize the cut by flowing it in the surface according to this simple speed function. Formulating this problem first in the smooth setting will yield an algorithm very different from previous approaches, which were geared towards texture mapping. The problem of surface cutting has many applications across geometry and graphics. Traditional techniques use cuts to store texture or other surface data in the plane, and then even apply signal processing or learning techniques on this data. Surface cuts are also important for fabrication, where a flat material like sheet metal, leather, or cloth is used to create 3D objects. Even more recently, fabrication with programmable matter enables complex designs at the microscale. Here, materials often have a very limited range of feasible stretching, imposing additional fabrication constraints. In all of these cases, cutting is critical because it allows us to find maps which have low distortion. Naively, a shape might need to be drastically stretched to map to the plane, but making just a few cuts, as you see here, dramatically reduces the distortion. In fact, we can always make more and more cuts to drive distortion arbitrarily low. This means that on its own, minimizing distortion is not even a well-posed objective, because we can always make more cuts to drive distortion a little bit lower. In fact, we seek cuts which not only induce little distortion, but also are not too long. This is very practical in terms of the previously mentioned applications. In fabrication, these seams might amount to assembly effort, which we want to minimize. Perhaps the initial instinct for how to formulate this problem is to say that the input is a triangle mesh and the cut is a collection of edges. Finding good cuts leads to challenging optimization problems. Even before we consider distortion, finding the shortest cut, which takes the surface to a disk, is NP hard. There have been many previous approaches to this problem, all in the context of texture mapping, including connecting paths between special vertices, iteratively growing regions of faces, or solving a combined optimization problem with continuous and discrete variables. All of these methods share the property that they're inherently discrete ways to think about the problem, rooted in identifying a set of edges in a particular triangle mesh. We will instead approach this problem in the smooth setting first, starting with a simple, continuous question. Suppose my surface is cut along the curve gamma and flattened into the plane. How does perturbing the location of this cut change the distortion of the flattening? Answering this question first in the smooth setting will lead to a natural and surprisingly simple algorithm for optimizing surface cuts, the results of which will have a very different character from previous approaches. For the fabrication applications discussed previously, this actually makes a lot of sense, because we want cuts that are more a function of the underlying geometry and less one of the particular input mesh we happen to have. So let's look at this continuous formulation. A first thing to note is that when mapping a surface to the plane, distortion is an inevitable fact of life. If the cut surface has any curvature, there will necessarily be some amount of distortion in any parameterization. It's not simply a matter of finding some perfect map. On the right, we visualize the different types of distortion for a local patch. Locally, a map might preserve areas, preserve angles, or more generally preserve neither, distorting both angles and area. One of the primary insights of our work is that this middle class of maps, conformal maps, which preserve angles, will allow us to apply techniques known as shape derivatives to the problem. And I really want to try to share the high-level picture as to why this conformal viewpoint really makes our whole method possible. Suppose we tried to work in the space of all parameterizations. There, we would be asking to place cuts to minimize the distortion of the minimally distorted map. But finding the minimally distorted map is already a hard, nonlinear optimization problem. On the other hand, when we formulate the same problem, working only in the space of conformal maps, finding the minimally distorted map amounts to simply a single linear solve. In turn, this simple form will allow us to use techniques from shape optimization to attack the problem. Even better, because the distortion corresponding to a cut is accessible via a linear solve, we can avoid representing the map at all in our optimization problem. The only degrees of freedom we will need are the location of the cut, and in fact at no point in our optimization will we ever need to actually compute any kind of flattening. And of course, at the end of the day, once we found these cuts, they're useful for any kind of parameterization or more general task, not just conformal mapping. What we're doing here is just leveraging conformal theory in order to efficiently optimize for the cut. The defining property of these conformal maps is that they preserve angle exactly, and so all distortion is in the form of a distortion of lengths. We can then quantify the distortion of lengths as a scalar function on the surface, which we'll denote by u. U gives the logarithm of the scaling of length by the parameterization. When u is negative, that means that lengths are shrinking. When u is positive, that means that they're stretching. And when u is 0, lengths are exactly preserved, which is what we want. And the amazing property of these conformal maps is that the scale factor u is governed by a simple Poisson equation. This says that the Laplacian of the scale factor is given by the Gaussian curvature of the surface. Of course, we must also specify boundary conditions for this equation, which in our case will always be u equals 0, corresponding to no stretching along the boundary. And remember that in this setting, the boundary for the PDE is really the location of our cut gamma. And something is really amazing has happened here. We hope to minimize distortion, and just as promised, the Yamabe equation gives us a way to read off the distortion corresponding to a cut without ever actually computing a flattening, simply by solving a linear PDE. Now that we have easy access to the distortion induced by any cut, we can choose an energy to penalize that distortion. To name a few, the Hanke energy corresponds to a strain energy for thin plate material stress. Dirichlet energy measures how non-constant the distortion is, or more generally, we can consider any form J of u. A first thing to note is that our approach applies generally to any of these kinds of energies. For the rest of this talk, I'll focus on the Dirichlet energy, simply because it has the most concise notation. Similarly, our desire for short cuts is easily captured by penalizing the length of the cut curve itself. On the right, I've shown some results of our method, where weakening the length penalty yields longer cuts with less distortion. Now, we're equipped to write down the smooth problem that we intend to optimize. We want to find a cut, gamma, which has little distortion and which is also short, where I've introduced the weighting parameter alpha sub L to denote the trade-off between length and distortion. And of course, this scale factor is subject to the Yamabe equation, which means that it describes a conformal flattening. This is really a different optimization problem than what we might be used to working with. Here, the unknown variable is not some vector of numbers, but the location of boundary conditions in a PDE. This isn't just something I can plug into my favorite optimization package. How do we optimize such a problem? As it turns out, the machinery of shape optimization has been developed for exactly this situation. In shape optimization, we seek a shape which minimizes some objective functions or satisfies some constraints. These techniques have been applied commonly within mechanical engineering, and more recently within the computer graphics community. As you might expect, the key ingredient in shape optimization is the shape derivative. And I think that the easiest way to understand shape derivatives is by example. Suppose we have a shape omega, as on the right, which we consider deforming with a perturbation sigma. Sigma is a scalar function along the boundary of the shape, where positive values indicate outward motion and negative values indicate inward motion. Now, for any quantity of interest, we can consider the shape derivative of that quantity with respect to the perturbation sigma. How does that quantity change as the shape deforms? For instance, let's consider the quantity area, just as an example. The shape derivative of area is given by the integral of sigma around the boundary. Where sigma is positive, the area is increasing. Where it's negative, the area is decreasing. And then the total change of area is given by the cumulative effect of these changes. So now back to our problem. We want to take the shape derivative of our distortion energy, but this is more challenging because the quantity inside the integral depends on the shape of the boundary itself, as captured by the Yamabe equation. With a bit more work, we can still evaluate the shape derivative by introducing Lagrange multipliers and showing that the shape derivative of the Lagrangian is the shape derivative of the constrained problem. When the dust settles, we'll see that the shape derivative of distortion is given by an integral around the boundary of the partial derivative of distortion squared times sigma. We are really surprised at how simple this formulation turns out to be. We're able to evaluate the change in flattening distortion induced by perturbing a cut via a relatively simple formula without ever actually computing a flattening. Now, as usual, once we can evaluate the change in a quantity with respect to a perturbation, we can minimize that quantity via a gradient descent in the direction of maximal change. This is our distortion cut flow. Similarly, we can take a short shape derivative of our other energy term, the length of the cut curve. This yields an integral of kappa sigma over the boundary, where kappa is the geodesic curvature of the cut. Once again, now we can minimize the length by flowing the cut in the direction of steepest descent. Note that this is just the well-known curve shortening flow. Putting this all together, to minimize our cut energy, which has a distortion term and a length term, we flow the cut in the normal direction, with magnitude given by the distortion shape derivative and the length shape derivative. Notice that the distortion derivative appears twice with opposite sign, because along the cut, there is distortion on both sides of the curve. Now that we've derived our flow in the smooth setting, we can express it as an algorithm on triangle meshes. Of course, there are many possible discretizations of this flow, and here we're just presenting one particular approach that we found to be effective. A first question to ask is how we represent the cut in the surface. Here, we represent the curve as an implicit level set of a sine distance function. One additional point to note is that in practice, we actually use a collection of such distance functions to represent more general configurations of curves. A few details about our discretization. Working on triangle meshes, we can represent all scalar quantities using piecewise linear hat basis functions at vertices, and build the Laplace operator via the usual cotan Laplacian when solving the Yamabe equation. One interesting challenge that arises in our case is that we need to solve these Poisson problems on various cut versions of the input mesh. To evaluate these systems, we explicitly cut the input mesh and temporarily construct new meshes with boundary introduced along the cut, on which we solve these Poisson problems. This is important to accurately estimate the partial derivative at the boundary, which is a key component of our flow. We found that simply using finite differences was not sufficiently accurate. Now we can walk through the steps to evaluate our flow and iteratively optimize a cut. Given a sine distance function phi, we extract the cut curve and split the mesh along the cut. We then solve for distortion in all of the induced patches and compute the flow velocity along the cut. We then harmonically extend this velocity across the surface, which is necessary because we're working with this implicit representation, and we then integrate the distortion term of the flow with a forward Euler step and the length term of the flow with a backward Euler step. Finally, we redistance the implicit function such that it remains a sine distance function. A few more concrete details. We use sparse direct Cholesky solvers for all linear solves, and the cost per iteration turns out to be dominated by solving 4 Laplace problems. But in fact, only one of these Laplace problems is actually new. The others can be pre-factored, and our cost is determined by factoring one new Laplace problem per iteration. We find a few hundred iterations to typically be sufficient, and putting this all together yields about 3 minutes of runtime on a 20K vertex mesh, as a typical example. One important point here is that we intentionally use the simplest numerical scheme, which effectively evaluates this new flow. There's surely a great deal of work that could be done in terms of fast solvers. Now some results, applications, and extensions of this method. First, we run our flow in a sphere, initializing the cut as a loop around the equator. We visualize the results on tennis balls, where pieces of flat fabric are stretched over hard rubber spheres. With a strong length penalty, our flow recovers the usual tennis ball geometry with 2 interlocking patches. Weaker length penalties yield alternative designs which have longer seams but even less stretching in the patches. Our method can also be applied without any special initialization. Here, various random and greedy strategies consistently yield good results. Our flow can also be applied to improve existing designs. Here, the seams of the volleyball are flowed to yield an alternative configuration which has both shorter seam length and less distortion in the patches. Now, we can also return to our motivating example, designing a collection of low distortion patches which could be used to fabricate a known geometry. Here we show the results of applying our method to this task, generating low distortion patches on a chair geometry. We can again adapt the strength of our length penalty to generate alternate designs. Here a longer cut yields a design which I think looks a bit more like a race car chair. Generally speaking, the designs generated with our smooth flow are noticeably similar to real-world geometries. Because our method is fully automatic, it can easily be used to generate families of cuts in response to variations of the shape. Once we have the basic formulation established, it's easy to modify it with various extensions. For one, we can prescribe symmetry constraints by simply imposing symmetry on the scalar functions which implicitly define the cut. We can also prescribe penalty functions on the surface, which discourage making cuts in certain regions. In this example, we've specified a penalty which discourages cuts through visible regions, leading a solution that hides the cuts wherever possible. Because we built our algorithm up from a smooth flow, we can also apply the optimization to more general settings than just the usual problem of decomposing a whole surface. For instance, here we consider optimizing for a single patch on the surface to have low distortion, where we don't care what happens on the rest of the surface. As a possible application, we show how the scheme could be used to design bandage patches on curved regions of the body, where the bandages need to cover a certain area but not stretch too much. In the limit of weak length penalty, our flow generates cut curves with density proportional to the Gaussian curvature of the underlying surface. We can leverage this limiting behavior to design smooth, space-filling curves by continually weakening and weakening the length penalty while running our flow. Here, we drive the flow with a constant right-hand side rather than Gaussian curvature to yield uniformly distributed cut curves. There's a lot of exciting work still to do. First, a theoretical question. Our flow is driven by the Yamabe equation, but this intrinsic equation actually only coincides with the extrinsic flattening of patches when the patches have trivial topology. For instance, consider flattening a cylinder, which has no intrinsic curvature but requires significant stretching to flatten. In practice, our algorithm has no topological restrictions. We easily handle this case by cutting non-disc-like patches as a post-process, which makes the cylinder easy to flatten. However, as a theoretical question, it's interesting to ask which PDE might properly model extrinsic flattening distortion for non-simple surface patches. A more practical question is that of global overlap. The lowest distortion parameterization of a cut surface might overlap itself in the plane. Our method is oblivious to this because we never actually compute a flattening. Recent parameterization tools allow the user to modify such patches to avoid global overlap, but it would be advantageous to incorporate this as a constraint in our optimization. We could also imagine integrating this flow into other problems where curves decompose a surface, like developable strip modeling or these zippable ribbons. In this work, we established a smooth formulation that models the surface cutting problem, but only scratched the surface of possible numerical methods. Areas of interest include more efficient and robust integrators, cut finite element methods for better discretizations, or leveraging the formulations of topological derivatives. Much like fluid simulation, we hope that a simple set of governing equations will yield a wide variety of effective numerical techniques. More broadly, in this work we found that transforming the problem of surface cutting using the tools from conformal geometry yielded a new smooth formulation, which could be tackled with shape optimization. We're optimistic that shape optimization could yield novel approaches for other problems in geometry processing. With that thought, I'll conclude. Thanks for listening.